Hello everyone, thank you for coming. My name is Javier Martínez. I'm research engineer at HopsWorks and also PhD at KTH. And in this talk I'm going to talk a lot about Python and also about the Lakehouse, what it is and how it extends the original Lakehouse to mitigate some limitations that it has. My voice is a little bit not perfect, but I hope you understand me well. So first of all, I want to remark that we can confirm already that Python is the language of data science, and that's because in the last days there was a report released by GitHub where they say that finally Python overtook JavaScript as the most popular language, and one of the reasons why is because of the search in data science and machine learning on GitHub. So basically Python is confirmed to be the language of choice for data science. However, there is a problem, and is that enterprises, when building machine learning systems, they normally use they build their machine learning systems on top of a lakehouse, but there are some limitations with the original lakehouse architecture, such as, for example, they don't have most of the existing lakehouse implementations don't have support for Python natively, and also the original lakehouse lacks some capabilities for real-time applications, and also it is commonly machine learning agnostic. So when you try to build AI applications on the traditional lakehouse, you might find some limitations. And one of the problems results in this kind of collaboration, throw it over the world, cross-team collaboration, where you have like walled gardens around different roles: data engineer, data scientist, and machine learning engineer, where the data engineer just pass the data as files to the data scientist that builds or trains on models using this data, and then pass the model to the machine learning engineer that is expected to put this model into production. And then in this scenario, the data scientists, as we mentioned before, they use mainly Python for all the operations. So what I would expect in the office is something like this, where data scientists mainly talk Python, but that's not the common language for data engineers and machine learning engineers. But what if we could use Python as a common language for all of them and try to convert this collaboration into more bucket brigade cross-team collaboration, where they speak the same language, and also enable data scientists to build machine learning systems by themselves, so they can go a step back and connect with data sources and process some data, and then train the models, and finally deploy these models into production and manage these models just using Python. So that's more or less the goal for this talk. So to achieve that, first we need to have a look at the Lakehouse architecture and some limitations that it has. So as a recap slide, we come from the data warehouses that show the benefits of separation of storage and compute, where you can scale both separately. And then with the Lakehouse architecture, now we have also separation between data and query engines. So you are able to pick the query engine that you want and also the AI platform that you want separately. And this is also mainly because of the open table format that helps supporting transaction management, so providing ACID guarantees and read and write of data from the Lakehouse tables concurrently. So this is more or less how the Lakehouse architecture looks like. But there are some limitations when it comes to building AI-enabled applications on top of the Lakehouse. So the first one is that, as I mentioned before, Python is a language of AI, but most of the existing Lakehouse implementations treat Python as a second-class citizen. And we can see this, for example, in the way of reading and writing data from the Lakehouse tables using Python. You might be able to do it, but under the hood, it's commonly used in JDBC or ODBC API. So this means that data that is located in the Lakehouse, normally in stored in a column-oriented format, needs to be pivoted to a row-oriented format to be transferred to the Python client, where you might be using pandas, polars, or TagDB that works on column-oriented data, so you need to pivot it again. So this serialization and deserialization, basically, you might not be aware directly, but you will see, you might experience higher latencies because of this pivoting. Then the second limitation is that the original Lakehouse lacks some real-time AI capabilities. So when you want to create or build real-time machine learning systems, there are two types of features that are commonly used or you might be dealing with. One is on-demand features that are basically features that are computed on demand using parameters that comes in the request when a prediction needs to be made. So for example, if you're going to make, if you want to detect if a transaction is fraud or not, when you make the payment, you send an event with the credit card number, and also you might want to send the location and the time that this transaction is going to happen. And then using this location and time, you might be able to basically create more features from them that will be passed to the model to try to make better predictions. So that would be one example. And then the other type of feature is basically pre-computed features that might be needed as well to enhance the model inputs when it comes to making the prediction. So in this case, if I use the same example as before, when I send the request with my credit card number and the location, I want to use the credit card number to retrieve information about my credit card and the recent activity. And these are basically pre-computed features that has to be available with low latency. And this cannot be achieved with the original Lakehouse architecture because latencies would be are too high to retrieve these features. So the third one is feature freshness is too high as well. So basically, for example, for a TikTok recommendation system, where you like a video and immediately you see recommendations based on the last video that you click, this kind of reactiveness is based on this feature freshness. So basically, new feedback or new events that are sent back to the system can be used later on and almost immediately to generate better predictions because the feature freshness is low. But that when you build this recommendation system on the traditional Lakehouse architecture, you cannot, or it's hard to achieve feature freshness that is not too high. So the third limitation for the traditional or original Lakehouse architecture is that it doesn't talk ML. So MLOps platform has been evolving separately from the Lakehouse, trying to provide better support for managing AI assets and also to create connections between your models and your data for serving the models and making inference and trying to monitor these changes, and also try to accommodate pipelines, ML pipelines for your in your system. but there has been a disconnection between the Lakehouse and this evolution of MLOP platform. So basically, there is this connection, which is a problem when you want to build machine learning systems on top of the Lakehouse. So, having said that, and the limitations, how can we kind of mitigate the limitations and move to the AI Lakehouse? So, some of, yeah, well, as you can see in the diagram, the AI Lakehouse tries to extend the traditional Lakehouse architecture with infrastructural services, such as a database for low latency retrieval of feature vectors, and also capabilities for model serving and model registry, and also vector index to enable the building RAG applications with retrieval augmented generation applications for GenAI. Also, it complements the traditional Lakehouse with tools for data, for monitoring data changes and model performance, and as well an AI query engine, which is basically tools or a service that helps you reading and writing data from the Lakehouse tables directly from Python without having this kind of serialization and deserialization that I mentioned before. And as well, tools or tools for accommodating AI pipelines on top of the Lakehouse. So, let me bring it here. Okay, now I will have I will focus on each of the layers and explain a little bit what we have been working on at HopSource to try to improve this extension of the traditional Lakehouse and how to improve the experience of operating in each of these layers using Python. So if we focus on the first layer on the bottom, so basically when you interact with each of the layers, you can do it via a Python API that we provide. So you can basically log into a project and get handles for the different services, like the feature store, the model registry, and so on. So if we focus on low latency retrieval of feature vectors, what you can do is to define your feature group, which is basically a group of features that make sense together. They are semantically related, and you basically pass through to the online enable parameter, which basically tells the AI Lakehouse that you want these features to be available for low latency retrieval. And then you create your feature view using this feature group, which will be used at the end in the model deployment, which is running online, and at prediction time to retrieve the contextual information for the credit card, for example, as I mentioned before, passing just the credit card number or other request parameters like location and so on. So this would be how to operate or how to retrieve low latency with low latency feature vectors for your online models. Then the same for registering models and deploying them. You can basically use the corresponding handlers via Python, and then for the vector index, you can create an embedding index. In this case is for news, and then you define specific embeddings. In this case, for the heading of the news, and create again a feature view where you pass your embedding index, saying that one of the features of the feature group is basically the type of embedding. So later on, what you can do is to find similar candidates based on a given embedding. You can basically retrieve from the feature group similar pieces of meaning. All right, then moving on to this next layer, data and model monitoring. Again, you should be able to do it with Python as well. So in this case, so there are different configurations that you can do, but the most common one is that you will have a feature group that contains the inference logs that are produced by your model that is running online. These inference logs are basically inputs and outputs of the model. So what you may want to do is to create a feature monitoring configuration on that feature group that defines two windows, detection window and reference window, which basically set the boundaries of the data that you want to use to compute the statistics on, and then compare it against each other. So in this case, we have a rolling window as a detection window, and then for the reference, you might prefer to choose a specific training data set to basically detect if the inputs and outputs of the model are diverging from your statistical properties of the trained data set that was used for that specific model. And then you can also specify how you want to perform the comparison. All right, then moving to the next layer, the AI query engine, and we built a query service that we call hot source query service using Apache Arrow, Arrowflight, and DarkDB that basically allows you to read and write data from the Lakehouse tables using Python without having to suffer from this pivoting between row-oriented and column-oriented format. So basically, the way it works is that when you use the hot source API, you try to read a batch of data or generate a training data set from the Python client. A query will be sent. So an Arrowflight client will be instantiated, and then a query will be sent to the Arrowflight server that will start an instance of DarkDB and will read from the Lakehouse tables directly and perform the query on top of that data. The query can be a specific query according to the data that you want to get in a batch fashion. Or if you are generating a training data set, it can be a point in time correct training data. So basically the result of the query will be transferred back to the client using ADBC protocol. So this means that once the data lands in memory on the client side and you create an instance of a bundled data frame, for example, pointing to that data, there will be zero copy from the data, so there is no duplication of the data. It will be created directly, and also you have not, you didn't need to really pivot between the different row-oriented or column-oriented formats. So we did some benchmarks on this using this query service, compare it with other cloud providers. And we found that we reached from 9 to 45 times the throughput that other cloud providers were offering. And basically, from a user perspective, the way to use this query service is basically more or less the same as I showed before, just using the hot source Python library. You can get access to your feature view, and you get batch data, and then all this process that I just described is happening under the hood. And also for creating the training data set, you can, again, on your feature view, call train test split, or there are some other options, and you will generate your training data. So we can mark this as text, like we can also do it in Python. And then last but not least, according to providing support for accommodating AI pipelines, the AI Lakehouse basically enables the creation of machine learning systems following the best practice of FTI pipeline architecture, which basically defines or classifies pipelines into three types: feature pipeline, training pipeline, and inference pipeline, to keep your machine learning system organized. So the first pipeline basically takes as input raw data and will output features and labels, create features and labels. So here is where your feature engineering will happen. Then the training pipeline will take these features and labels as input and output a trained model. And finally, the inference pipeline basically takes the trained model, will take features, and also will take from the downstream application some request parameters or request data, and perform a prediction. So the output will be predictions that will be sent back to the client and also back to the AI Lakehouse for later monitoring. So to wrap up, as we commented at the beginning of the talk, most of the existing implementations of the Lakehouse architecture show some limitations when it comes to build AI-enabled applications, and this leads to this kind of collaboration where we have these walled gardens around the different roles, and Python is mainly used only on the middle part of the data scientists, and using the AI Lakehouse that basically improves support for Python or treats Python as a first-class citizen, and also understands machine learning. You can enable data scientists to build machine learning systems just using Python, so involving all the steps in the creation of the or design of your pipelines for the different parts of the system. So, yeah, that would be. All right. So, thank you very much for listening. And yeah, if you have questions, just I'm happy to take them.
Any questions?
Yeah.
I was curious, like, for example, on the previous slide, you have an example. So for the first part, where, like, I guess it's the data engineer or somebody doing that def geotime, and then you're doing that g.insert df, is the computation of, like, does HopsWorks ever help you to push the computation of that part to the Lakehouse, or that is up to the data engineer still?
So you can choose, basically, like you can have the compute inside, or you can have it external. Like it's up to you, basically. It doesn't push you to bring the computation on the Lakehouse.
So sorry, to be more clear, like, can that feature calculation, the feature computation, like the actual like creation of the feature, happen within, like, from Python within HopsWorks platform, or is HopsWorks more just retrieving the, like, once the feature is there, it's more retrieving and handling the ML AI workloads, or helping you with the ML AI workloads
So
on the Lakehouse downstream?
Yeah, sorry. So HopsWorks provides tool for you to do the computation on HopsWorks, but it's not required. So, like, you can have the computation somewhere else, and then just write to the, like in this case, insert to the feature flux directly. So if you have the computation somewhere else. But that's for the feature creation at the first steps. Then, yeah. I'm not sure if I answered the question. Did I? more or less.
Yeah, I think to a good extent. I can ask you later, like in more depth.
We'll take a couple more questions.
Could you go back to the slide that has import houseworks? Could you go back to the slide that has import houseworks at the top? So this might be related to the question that you asked. I'm not asking about compute. It's more about like for that first code snippet for future serving TV, are we sort of imagining that the person who is writing that code is basically like a platform engineer who is configuring the underlying storage tables? Because for example, like the line that says online enabled equals true. So my understanding of like Apache Hootie and Iceberg and kind of the like the table part is that like in order for online enabled to be possible, that first has to be configured on the table side, like at the Hootie or Iceberg layer. So I'm curious, like, is the idea that that first set of code is like a setup, initial setup part, or is this actually, or is this part of the AI workflow?
So we implemented also a system for synchronization of the feature values between the offline, between the Lakehouse to the database for certain features. So this synchronization I didn't include here, but basically when you create, you define your feature group and you specify that you want the features to be available for online cases, then we basically synchronize the values to an operational database or key-value store, and then basically we manage this mapping between both. And then when you want to access the features, we go directly to the corresponding database. So it's not something that data scientists have to deal with like directly. They just care about defining the feature groups and.
I see. So there's kind of some initial work that's been done before this to initialize all of the Hootie tables, for example, so they're set up to do change data capture,
Yeah.
so that they can support like an online experience.
Yeah. So this there are tools under the hood that are doing this kind of things. Yeah.
Okay.
But I didn't include it here. But yeah. So this is like the highest level, like just the user from the user perspective.
Thank you.
Hi, great presentation, thank you by the way. A quick question, you had a slide showing the comparison between HubSpot with Databricks and SageMaker. Yes, that one. So under the underlying engine, what do you compare it with? Let's take Databricks, for example. They released, for example, the photo engine. Right? It's supposed to be like super fast, super optimized. So what did you compare? What's the comparison here exactly in terms of instance and engine?
So this was done. So we saw these benchmarks on a paper that was released earlier this year. So these benchmarks are from like beginning of this year, kind of. So by that time there was not this new implementation of database. But so in this case, we are basically using kind of the default setups for the different cloud providers and for the different feature stores of the different cloud providers, and then performing the same kind of operations for bringing from one feature group or three different feature groups with the join.
Thank you.
Yeah.
Any more questions? Okay, thank you.
Thank you.